In the last lecture, I introduced the Einstein equation, g mu nu equals 8 pi g over c to the fourth t mu nu. On the left-hand side, we have the Einstein tensor. And on the right-hand side, we have the stress energy momentum tensor. And g is, of course, Newton's constant, and c is the speed of light. So the Einstein tensor is obtained from the Riemann tensor, and so it contains the metric, first derivatives of the metric, and second derivatives of the metric. The stress energy momentum tensor, on the other hand, is built from the metric and the matter fields, and typically it doesn't involve derivatives of the metric. So it involves g mu nu and matter fields. In this lecture, I plan to discuss in some detail the stress energy momentum tensor. Now, throughout this lecture, I plan to keep factors of c. In other words, I'm not going to set c equal to 1 like I have often done in previous lectures. Of course, the value of c, whether it's 1 or not, just depends on your choice of units. But when we choose c equal 1, we're choosing to measure spatial distances and time intervals in the same units, and this tends to obscure the distinction between physically distinct quantities such as energy and momentum. I want to begin by reviewing some key results from special relativity. So we'll of course use Minkowski coordinates, x mu, so here's a space-time diagram. This is the x0 axis, and x0, the coordinate x0 is related to proper time t along this world line by x0 equals c times t. And this is the x1 axis. And just to keep things simple, we'll assume there's only two space-time dimensions, so there's no x2 or x3 axis. So here's a particle moving through the space-time with world line x mu of tau. And now the forward velocity of the particle is defined as always as the partial of x mu of tau with respect to tau. And we can write this as partial x0 with respect to tau, comma, partial x1 with respect to tau. And because x0 is c times t, we can write this as c times partial t with respect to tau, comma, partial x1 with respect to tau. Now pull this factor, partial t with respect to tau, outside. We have partial t with respect to tau times c, comma, this term by the chain rule we can write as partial x1 with respect to t. Now this is just the ordinary velocity of the particle as seen by an observer at rest in this frame. In other words, an observer just traveling up the t-axis. So we'll denote that as v. And this factor, partial t with respect to tau, can be determined from the line element. So the line element is, of course, ds squared is eta mu nu dx mu dx nu, where eta mu nu is the Minkowski metric, minus 1, 1, 1, 1 down the diagonals. So this is minus dx0 squared plus dx1 squared, and we're just working in two dimensions here. Now remember, x0 is c times t, so this is minus c squared dt squared plus dx1 squared. And the proper time separation between nearby events is defined as minus ds squared over c squared. So that's equal to dt squared minus dx1 squared over c squared. Now if I pull out a factor of dt squared, we have 1 minus partial x1 with respect to t quantity squared over c squared. This, of course, is just v, so that's equal to dt squared times 1 minus v squared over c squared. From this result, d tau squared equals dt squared times this factor. We find that dt squared over d tau squared is equal to 1 divided by 1 minus v squared over c squared, or partial t with respect to tau equals 1 divided by the square root of 1 minus v squared over c squared. This, of course, is the relativistic gamma factor. So from here we see that the forward velocity of the particle can be written as gamma times c comma v. So the particle forward velocity is u mu equals gamma times c comma v. And just to emphasize that this is the forward velocity of the particle, I'm going to put a little subscript p here, and also on gamma and v. Since this is the velocity of the particle, it's the ordinary velocity of the particle as seen by an observer who's traveling along the t-axis in these Minkowski coordinates. Now, from the forward velocity, we can define the forward momentum. So that will just be p mu, and I'll put a subscript p on there for particle. That's m times u mu. So that's m gamma times c comma vp. Now, the observer who sees the particle is moving with the velocity v sub p is the observer at rest in this Minkowski frame. In other words, the observer who's moving right along the t-axis. So this is the observer moving up the x0 axis, and this is the particle. So this observer has forward velocity, and I'll sometimes use a script O for the observer. The forward velocity of this observer is just c comma 0. Now for this observer, the set of events that are seen as simultaneous are events that lie along a horizontal line in this diagram. In other words, there are events that lie in the direction of this basis vector. This is the vector d by dx1, and we'll call this vector e1. All right, so this is the basis vector pointing in the x1 direction, and of course the vector here pointing in the x0 direction is just the forward velocity of this observer. So in addition to the forward velocity, the observer also can make use of this basis vector that has components 0, 1 to define the space-like directions. The questions we'd like to ask and answer are: what are the energy and the ordinary 3 momentum of the particle as seen by the observer O? In other words, the forward momentum encodes the energy and the ordinary momentum of the particle, and we would like to know how this observer extracts the energy and the 3 momentum from the 4 momentum. And the answer is that the observer just takes the dot product of the 4 momentum with these basis vectors. So the energy, we'll call it E, is, well, there's a minus sign in here, the dot product of the particle momentum with the observer's forward velocity. And the ordinary 3 momentum, we'll just call that P sub 1. If we were working in 3 spatial dimensions, there would be a P1, P2, and P3. This is just the dot product between the forward momentum and the spatial basis vector. So let's work this out. Remember, the dot here is the Minkowski metric, -1, 1 down the diagonals. So when we multiply that times u, we have a minus c comma 0. But the minus sign will cancel this minus sign. and leave us with m gamma times c times another factor of c. So that's mc squared times gamma sub p. And similarly, multiplying this E1 by the Minkowski metric doesn't change anything. It's still 0, 1. Matrix multiply that times this vector, and we have m v sub p gamma sub p. So these results should be familiar from special relativity. This is just the energy of a particle moving with velocity v. It's the rest energy, mc squared, times the relativistic gamma factor. And this is the relativistic momentum of the particle, the ordinary momentum we have from Newtonian mechanics, m times v times the relativistic gamma factor. Written this way, these are the energy and 3 momentum of the particle as seen by any observer, not just an observer who's at rest in this Minkowski frame. And to emphasize that point, let's take a look at an arbitrary observer. So here's our Minkowski diagram, the x1 axis, the x0 axis, our particle moving with 4 velocity u sub p, and we'll take our observer to be moving with some 4 velocity u, and we'll take that 4 velocity to be gamma c comma v, where v is the velocity of the observer as seen in this Minkowski frame. In other words, the velocity of this observer is seen by some observer who's at rest and moving along the x0 axis. And now, what about the spatial basis vector that this observer uses? So, this is the vector E1. So, it turns out that this is just gamma times v over c comma 1. And you can check that these vectors form an orthonormal basis. So check, for example, E1 dot E1 is 1. E1 and U are orthogonal, so E1 dot U is 0, and U dot U is minus c squared. Now recall that the momentum, the 4 momentum of the particle, is equal to the mass of the particle times gamma for the particle times c comma the velocity of the particle. So according to our prescription, we can compute the energy of the particle as seen by this observer as just the minus the dot product of the particle 4 momentum with the observer's 4 velocity. So let's work this out. This is minus m gamma sub p c comma v sub p times the Minkowski metric, that's minus 1001, times u, which is gamma times c comma v. And just to make sure this is clear, I'm going to put a little subscript O for observer on the gamma and the v here. So this is gamma sub O times c comma v sub O. So now simplifying, we have minus m times gamma sub p times gamma sub O times c comma v sub p, and the Minkowski metric times this vector gives minus c comma v sub O. So this is minus m gamma p gamma O times minus c squared plus vp vo. And we can pull out a factor of minus c squared here, and this minus then cancels that minus. We have mc squared times gamma p gamma O times 1 minus vp vo over c squared. So what is this complicated factor? Well, I claim this is just the relativistic gamma factor for the particle as seen by the observer O. So let me call that gamma sub PO. So that's equal to 1 divided by the square root of 1 minus the velocity of the particle as seen by the observer O, that's V sub PO, squared divided by C squared. And we can verify this by using the velocity addition formula. If you'll recall, the velocity addition formula tells us that the velocity of the particle as seen by the observer O is equal to the velocity of the particle in the rest frame, the Minkowski frame, minus the velocity of the observer in that frame, divided by 1 minus Vp Vo over c squared. You can now check for yourself that this combination equals gamma sub Po. Just insert this result for the velocity in here and simplify, and you'll see that you have exactly the same expression. It just requires a bit of algebra. So the result is that the energy as seen by the observer O is, this is the definition. It's minus P of the particle inner product with U of the observer, and I'll go ahead and put a little subscript O there, and that's equal to mc squared times gamma sub Po, the gamma factor for the particle as seen by the observer. We can carry out a similar calculation to obtain the 3 momentum as seen by the observer O. So the 3 momentum, call that P1, is equal to the inner product between the particle momentum and the basis vector E1 carried by the observer. So remember, the 4 momentum of the particle is m gamma p times c comma vp. The Minkowski metric is minus 1001, and the basis vector E1 is gamma, that's gamma of the observer, times v of the observer over c comma 1. So if we multiply this out, we have m gamma p times gamma o times c comma vp, and then minus vo over c comma 1. And this simplifies to m gamma p gamma o times minus vo plus vp. Now if you'll recall from above, vp minus vo is vpo times this factor. So we have m gamma p gamma o vpo times the factor 1 minus vp vo over c squared. But now gamma p gamma o times this factor is gamma po. So what we're left with is P1 is equal to m vpo times gamma po. So this result shows that the 3 momentum of the particle, as seen by the observer, is the inner product between the 4 momentum and the observer's basis vector E1, and that's m times the velocity of the particle as seen by the observer times the relativistic gamma factor. So the way that any observer extracts the energy and 3 momentum from the particle 4 momentum is by taking an inner product with the basis vectors u and e. Now, there are a couple of relationships implicit in these results, and I'd like to point them out because they'll be useful later on. If we insert the particle mass times 4 velocity in here for the particle 4 momentum, then the mass cancels the mass here, and what we're left with is the following result. The inner product between the particle 4 velocity and the observer 4 velocity is minus c squared times the relativistic gamma factor of the particle as seen by the observer. And similarly here we can insert m times the particle 4 velocity. The m's cancel the m's here, and what we're left with is u sub p dot the basis vector E1 is equal to the velocity of the particle as seen by the observer times the gamma factor. And by the way, it should be pretty obvious that if we were working in 3 spatial dimensions rather than 1, then this E1 would be EI, and this velocity would be the ith component of the velocity. So let me write that as VI comma PO. So this is the ith component of the velocity of the particle is observed by the observer O. And now let me collect these results along with our basic definitions of the energy. That's minus the 4 momentum of the particle, inner product with the observer's 4 velocity, and the 3 momentum. And now I'll use p sub I if we're working in 3 spatial dimensions, where I ranges from 1, 2, and 3. This is the inner product between the particle 4 momentum and the ith basis vector. Let me draw a picture to go along with this summary. So here's the particle, P, and here's the observer, O, and the particle, of course, has a 4 velocity u sub P. The observer has a 4 velocity u sub O, and the observer also carries along a set of basis vectors, E1, E2, and there's a third basis vector, E3, that I won't try to draw on this diagram, but E1, E2, and E3 are orthogonal to the observer's 4 velocity. So these basis vectors, the EIs, span a set of events that the observer sees as simultaneous. In other words, a set of events that are space-like for that observer. All of these results were derived in the context of special relativity, but you'll notice they're written here in a way that's independent of the coordinate system used. So, by the principle of equivalence, all of these results can be elevated to curved spacetimes, and they hold in that context as well. So the principle of equivalence tells us that these results hold in curved spacetime. So now, keeping these results in mind, let's turn to the interpretation of the stress-energy momentum tensor. So we have an observer, O, with 4 velocity u mu, and I won't bother to put a subscript O on that, and spatial basis vectors E mu sub I. There are 2 main definitions. The first is what I'll call curly P mu. This is minus 1 over c squared times T mu nu, the stress energy momentum tensor, times u nu, the 4 velocity of the observer O. And this is the 4 momentum density. In more detail, this is the 4 momentum of the matter fields, or the non-gravitational fields, per unit volume, but it's per unit of the volume is seen by O, so we'll call this O's volume. And the other definition is, I'll call it curly F mu sub I. So this is a set of vectors, 3 different vectors. This is stress energy momentum tensor T mu nu E nu I. And this is the 4 momentum flux. So in more detail, it's the 4 momentum of the matter fields per unit O's time. So that's time on O's clock per unit O's area. Area is measured by O, crossing the surface with normal vector E mu I. So P mu is the form momentum density, F mu I is the form momentum flux. And as we've seen before, if the observer wants to extract the energy or 3 momentum from one of these vectors, they just need to contract with either the 4 velocity, their own 4 velocity, or one of their spatial basis vectors. So for example, the energy density is defined as minus the 4 momentum density inner product with the observer's 4 velocity. And putting that together with this definition gives 1 over c squared t mu nu u mu u nu. And likewise, the 3 momentum density is just the 4 momentum density contracted with the spatial basis vector EI. So putting that together with the definition, we have minus of curly p, we have minus 1 over c squared times t mu nu u mu e nu I. And now from the 4 momentum flux, the observer can define an energy flux. That's just minus the contraction of F with U, and using that with the definition of F, we have minus T mu nu E mu I U nu. And finally, the 3 momentum flux is defined as the inner product of F I with EJ. So that would be T mu nu E mu I E nu J. This is a momentum flux, so it's the rate at which the ith component of momentum crosses a unit area with perpendicular given by E sub j. And similarly, this energy flux is the rate at which energy is crossing a unit area with normal given by E sub I. And the 3 momentum density is the density of the ith component of momentum. So these are our basic definitions that give physical meaning to the stress energy momentum tensor for the observer O. What I'd like to do next is spend some time working through a specific example to help make sure these definitions make sense. So recall that a perfect fluid has stress energy momentum tensor given by the mass density mu times u mu u nu, that's for the fluid, plus the pressure times g mu nu plus u mu u nu for the fluid, and we're keeping factors of c in all of our equations in this lecture. So what I want to do is to make things especially simple, I want to choose an equation of state that says that the pressure is always 0. So the equation of state choice is simply P equals 0. So this is a pressureless fluid, and this is sometimes referred to as dust. So I'll write the stress energy momentum tensor as the mass density times u mu u nu with a little superscript d for dust. Just another name for a pressureless perfect fluid. So let's apply our definitions to this example of dust. And let's start by returning to these basic definitions of the 4 momentum density and 4 momentum flux. So first, the 4 momentum density. That's P mu equals minus 1 over c squared times T mu nu u nu. And inserting the stress energy momentum tensor for dust, we have the mass density mu times u mu for the dust, I'll put the little subscript d downstairs since the index is upstairs, times u of the dust inner product with u of the observer. If you'll recall from earlier in the lecture, we showed that the inner product of two four velocities is just minus c squared times the relativistic gamma factor between the two. So this would be the gamma factor for the dust as seen by the observer. So this minus c squared cancels the minus 1 over c squared, and we see that the momentum density is just the mass density times the four velocity of the dust times gamma. Now mu is the mass density. It's the rest mass per unit rest volume. So if I have a little packet of dust, then mu is the rest mass contained in this region divided by the volume of this region as measured by an observer for whom the dust is at rest, a co-moving observer. So I'll just refer to this as the mass over the volume, with it understood that this is rest mass divided by the rest volume. And now, putting this together, we see the four momentum density can be written schematically as the mass, that's the rest mass, times the four velocity of the dust divided by the volume over gamma. And now for the observer O, who sees this moving past with some speed v, this volume is Lorentz contracted along the direction of motion. So the volume will be smaller by a factor of gamma, and that's this factor of gamma. So this is equal to the mass, the rest mass, per unit of O's volume times the dust four velocity. But the rest mass times the four velocity is just the four momentum. So this is the four momentum divided by O's volume. So that's just as we expected. P mu is the four momentum density, and it's the density in the sense of per unit of O's volume. And now if we contract P mu with the observer's four velocity and throw in a minus sign, we know that the four momentum contracted with U with a minus sign is just the energy. So this is energy per unit of O's volume. And P contracted with one of the basis vectors EI, four momentum contracted with EI is just the three momentum. And that would be three momentum per unit of O's volume. Now let's take a look at the four momentum flux. If we recall, the four momentum flux is just defined as T mu nu E nu I. So that's F mu I equals T mu nu E nu I. But T mu nu is the mass density times U mu of the dust, U nu of the dust, E nu I. And now if you'll recall, this combination is just the ith component of the velocity as seen by the observer O times gamma, the gamma factor of the dust as seen by the observer O. So we can write this as, again, M is just the rest mass per unit rest volume, and that's times U of dust times VI gamma. And let's regroup these terms a bit. This is the mass times the dust four velocity, and that will give the four momentum, times VI divided by the volume over gamma. So let's take a look at the flux in, say, the E1 direction. So this would be the 4 momentum, the muth component, times V1 over the rest volume divided by gamma. That's the volume as seen by O. And V is the velocity of the dust as seen by O. So it's the distance the dust travels, let's just call that delta x, divided by the time it takes to travel that distance. Let's call that delta t. So that's delta t on O's clock and delta x as measured by O. So let's draw a picture here. This is a packet of dust, and it's a side view from O's perspective. So O's side view. And this is the surface on the right side with normal E1. And this packet has width delta x and cross-sectional area A. All right, so during time t, all of the dust that's in this region passes across this surface. So here's the dust. So all the dust within this volume crosses the surface in time delta t. And that's true because the dust is moving with velocity, or with one component number 1 of velocity equal to delta x over delta t. So even the dust that starts over here on the far side of the packet has just enough time to reach that surface in time delta t. So what this diagram shows us is that the volume as seen by the observer O, this volume divided by gamma, is equal to delta x times A times delta x. So inserting that in here, we find F mu1 is equal to the 4 momentum muth component times delta x over delta t times O's volume, which is delta x times A. So that's equal to the 4 momentum per unit O's time and area. So more generally, we can write F mu I as the 4 momentum muth component divided by the time interval on O's clock times the area that's perpendicular to the basis vector EI. So this is, as it should be, the 4 momentum flux. Flux is seen by the observer O. And if we want to extract the energy, we just contract it with the 4 velocity of the observer O, and that picks out the energy part of this 4 momentum, and it gives us the energy flux. And if we'd like the momentum flux, we just contract it with the jth basis vector. And this gives us this picks out the 3 momentum part of the 4 momentum and leaves us with the 3 momentum flux. More precisely, this would be the jth component of momentum flux across the area perpendicular to the ith basis vector. Let me summarize once again the general definitions. We have the 4 momentum density, that's minus 1 over c squared t mu nu u nu, it's 4 momentum density. The 4 momentum flux is t mu nu e nu I. That's the 4 momentum flux in the I direction. The energy density is then minus P dot U, which is 1 over c squared T mu nu U mu U nu. The momentum density, or the I component of momentum, let's call that I momentum, that's equal to P dot EI, which is minus 1 over c squared times T mu nu E mu I U nu. The energy flux in the I direction is minus F mu I dot U, delete that index, F dot U, and that's equal to minus T mu nu U mu E nu I. And finally, the momentum flux, we'll call this the J momentum. So the Jth component of momentum flux in the I direction is equal to F I dot EJ. So that's T mu nu E mu I E nu J. Now all of these results are valid in any coordinate system, but they're especially simple if our observer uses Fermi normal coordinates. Recall that Fermi normal coordinates are defined by an observer traveling along a geodesic. The observer carries a set of spatial basis vectors, E1, E2, I'll go ahead and draw E3 here. These basis vectors are orthonormal, they're orthogonal to each other, and they're normalized, and they're orthogonal to the forward velocity of the observer. And the observer uses these 4 basis vectors to construct a set of coordinates for events near the world line. And in those coordinates, let's call the coordinates say x bar mu to distinguish them from our generic space-time coordinates, which are just x mu. So in these coordinates, the metric has the form of the flat space-time metric plus terms that are quadratic in the spatial x's. Call those x bar i's. Now, it was quite a few lectures ago, but we actually worked out explicitly the relationship between the generic space-time coordinates and the Fermi normal coordinates. So this coordinate transformation was given by just the coordinates along the world line, so along this geodesic, plus x bar I EI mu minus 1/2 Christoffel symbols, mu alpha beta, x bar I, x bar j, E alpha I, E beta j, plus higher order terms. And in this expression, these quantities, the coordinates of the world line, and also the basis vectors, the EIs, EJs, the Christoffel symbols, all of these things depend on the proper time along this geodesic. So they depend on x bar 0, the 0 coordinate. And from this, we worked out the derivatives of the old coordinates in terms of the Fermi normal coordinates. So we found partial x mu with respect to x bar 0 is equal to u mu over c plus terms linear and higher in the x bar i's. And by the way, I probably didn't include the factors of c when working it out before, but if you go back and repeat the calculation with the factors of c in place, you'll see that this is the forward velocity of the observer divided by c. And we also worked out the derivative of the old coordinates with respect to the new spatial Fermi normal coordinates, and this is just e mu I plus higher order terms, linear and higher, in the x bar i's. Now, the reason I'm writing down these results is to help make clear something that might be obvious to you anyway, and that is that these basis vectors in Fermi normal coordinates, the components of these vectors are all ones and zeros. So, for example, if we look at the forward velocity, let's look at it as a covector in Fermi normal coordinates, so the barred components of u sub mu, this is equal to partial x nu with respect to x bar mu u nu. So this is just the coordinate transformation between the generic coordinates, unbarred coordinates, and the barred coordinates for a covector. So this tells us if we take the mu equal to 0, this is partial x nu with respect to x bar 0 u nu, but that from here is just u nu over c plus higher order terms times u sub nu. And of course the forward velocity contracted with itself is minus c squared, so that's minus c squared over c, which is minus c. And the other higher order terms here don't matter because we're really evaluating this along the world line. We're asking for what the components are of the forward velocity of the world line, and it's only defined on the world line. So here we're setting all the x bar i's, the spatial coordinates, equal to 0. So all these terms go away. So x bar sub 0 is minus c, and likewise the spatial Fermi normal coordinate components of the forward velocity are just partial x nu with respect to x bar I u nu. That's e mu, or rather e nu I, and higher order terms u nu, but the e's are orthogonal to u, and the higher order terms vanish because we're setting x bar I is equal to 0, so this is just 0. So this tells us that in Fermi normal coordinates, the forward velocity with index down is minus c 0, 0, 0. And now we can raise the index using the metric, which is just eta mu nu along the world line, and conclude that the forward velocity in Fermi normal coordinates is c, 0, 0, 0. And now we can do a similar calculation for the spatial basis vectors. For example, E1, and now I need to move the index down. And let's look for the Fermi normal coordinate components of E1 with a down index. This is partial x nu with respect to x bar mu E1 nu. And setting the index mu equal to 0, we have E1 0 equals partial x nu with respect to x bar 0 times E1 nu. And this is just u nu over c plus higher order terms times e nu 1. But u and e are orthogonal, and these higher order terms vanish because we're setting x bar I equal to 0. So this is just 0. And for the spatial components of E1, this is partial x nu with respect to x bar I E1 nu, which is, this is E nu I plus higher order terms times E1 nu. And now this, because the e's are orthogonal, this is just delta I1. and the higher order terms again go away. So what we see is that E1 mu in Fermi normal coordinates is the zeroth component is 0, and the spatial components are just 1, 0, 0. We can now raise this index using the metric in Fermi normal coordinates, which is just eta mu nu. So this is 0, 1, 0, 0. And likewise, the basis vector 2 has components 0, 0, 1, 0 in Fermi normal coordinates. And basis vector number 3 has components 0, 0, 0, 1. So as claimed, the 4 vectors that the observer uses to construct Fermi normal coordinates have components that are just 1s and 0s, or in this case c's and zeros, when the components of those vectors are expressed in Fermi normal coordinates. By the way, in the earlier lecture where I constructed Fermi normal coordinates, I assumed that the world line was a geodesic, but it's possible to construct Fermi normal coordinates even if the world line isn't a geodesic. It's a little bit more complicated, and the result is that there are some linear terms in the x bar i's and in the metric near the world line, but that doesn't actually change any of our results here. It's still true that the forward velocity of the observer and the basis vectors of the observer, when expressed in terms of Fermi normal coordinates, are just c's and zeros and 1s and zeros. So we can use these results even if the observer is accelerating. So let's return now to our general definitions for the stress energy momentum tensor and write these definitions in terms of Fermi normal coordinates. So this first one for the energy density, in Fermi normal coordinates I just simply put bars on each of these tensors, and then u bar mu, u bar nu are each just c equal to c, 0, 0, 0. So the two factors of c cancel the c squared here, and we're just left with the 0, 0 component of t in Fermi normal coordinates. And this, we have a factor of c coming from here that cancels one of those. And E mu I is in the sum over mu, the only term that's non-zero is when mu is equal to I. So this is just minus 1 over c ti 0 in Fermi normal coordinates. And for the energy flux, we have a factor of c coming from here. So this is minus c times t 0 I. And finally, this is t, and that's t bar. It's in Fermi normal coordinates. And this is t bar ij. So the blue results here use Fermi normal coordinates. And in those coordinates, the 0, 0, 0i, and ij components have direct interpretations as energy density, momentum density, energy, and momentum flux. There are still some important aspects of the stress energy momentum tensor that we need to discuss, but I think I'll save them for the next lecture. In particular, you've probably noticed that the I momentum density and the energy flux in the I direction are essentially the same apart from factors of c. So we need to discuss that. We also, you might notice because of the symmetry of the stress energy momentum tensor, that the j momentum flux in the I direction is the same as the I momentum flux in the j direction. So that's something else that needs to be understood. And you'll also notice that even though T mu nu is referred to as the stress energy momentum tensor, I haven't discussed stress at all. So we need to talk about where stress comes into play. And the last thing that I want to talk about in the next lecture is the sense in which the stress energy momentum tensor is conserved.